Okay, well, we've just shown that under some conditions, particles can tunnel through a barrier potential, even though classically there's no possibility of transmission. But does this really happen? Can electrons or other particles really pass through barriers like this? Well, here, we're going to do an example, and I just want to motivate it a little bit to show you that actually this is a rather common circumstance. Of what I have here is just a digital voltmeter, much like the ones that you've been sent. And right now it's set to measure electrical resistance, and it's on the 200 ohm scale, okay? Here's a piece of aluminum foil. As you can imagine, aluminum is a very good conductor. It's one of the uh, materials that has the highest conductivity, okay? And so if I connect the probes to the aluminum, you should see, there we go, that the resistance is very low. It's on the order of a few tenths of an ohm across this strip of metal, okay? Nothing could be simpler, right? Except that there's something odd about this. Aluminum also has the property that it's very reactive, and when it's exposed to air, it oxidizes almost instantly, forming an oxide that's a few tens of angstroms thick. The aluminum is very tough. The aluminum oxide is very tough. In fact, aluminum oxide, another name for it is sapphire, okay? So it's a gem material, very tough and very insulating. How do the electrons in the demo we just did, how did they cross through that insulating layer in order to flow through the aluminum? Something to think about. Okay, so here's the problem that we're going to investigate. It's similar to the barrier potential problem that we did before. We're just going to put in some values now. And we're going to try to investigate electrons in aluminum crossing through an aluminum oxide barrier. Okay? Very good. And we'll assume that our barrier has some width L, and that electrons are incident from one side. And we know that many of these might be reflected, but we'd like to know what's the possibility that electrons will get through. Okay? And to do this problem, we're going to put in numbers. And the numbers I'm putting in are made up, but they're reasonable numbers. They're not that far off, but I didn't want to be bothered to look up exact quantities. We'll assume that the electrons behave like particles with a mass of the electron mass. We'll assume that the barrier height is about 10 electron volts, which is about right for an oxide. And we'll assume that the kinetic energy of the electrons is about 7 electron volts, which represents the Fermi energy in the aluminum, okay? And from this, we can calculate a couple of things. First of all, we can calculate alpha, which remember is square root of 2 times m times u naught minus e divided by h bar, okay? And secondly, we can calculate this factor, which we'll also need in order to do our calculation. Okay, I'm going to let you go ahead and calculate those things and put up a reading question for you to give your answers. 1 sec. Okay, and what you should have found was that alpha was on the order of 10 to the 10 inverse meters, which is this equivalent to saying that the penetration depth is about 1 angstrom, okay? On the other hand, this factor here, 16e minus u over u squared, evaluates to about 3.3. Okay, these values will be useful when we go ahead. 1 second. Okay, ready? Now let's evaluate some transmission probabilities for different values of L, okay? So I'm going to make a table here. For different values of L, we'll compute first alpha times L, and then the transmission probability. And finally, we'll we'll predict a current based on a couple of assumptions. You'll see in one moment. So let's investigate some different distances. L equals 2 angstroms, 5 angstroms, 10 angstroms, and 40 angstroms. 40 angstroms, still pretty small, right? All right, so in this case, what's alpha L? Well, alpha, we said, is about 10 to the 10, and an angstrom is 10 to the minus 10 meters. So the combination of this gives 2, 5, 10, and 40. And now we can figure out what the transmission coefficient is. So for each of these, all we have to do is to do the calculation. Using the tunneling formula we wrote down a moment ago. Let me just bring that up again. Okay, there we are. So here, let's go through the first value together. If alpha L is equal to 2, then in this expression, the exponential factor is e to the minus 2 times 2, e to the minus 4. Okay, which is 0.018. And then we should multiply by the factor in the brackets, which essentially is multiplying this by 3.3. And what we get is 0.06, okay? Or about a 6% probability for transmission, okay? Already seems small, but you know there's such a high density of electrons in the metal, okay? That even if most of them are turned back each time they try to cross, there are so many and they're moving so fast that we could still get an appreciable current through. In fact, suppose we set things up in such a way that under this condition, we get a current of 1 ampere, okay? Then what happens as we make the barrier thicker? Well, that's what we're gonna figure out next. And you'll see that we get a very strong dependence on length. So now, in the same way, we can find the transmission probability for a 5 angstrom barrier. It works out to be 1.5 times 10 to the minus 4, okay? So if we had 1 amp in the first case, we would only have 2.4 milliamps transmission for a 5 angstrom barrier. For a 10 angstrom barrier, the transmission is much smaller. And the reason is because of this exponential factor here, okay? E to the minus 2 alpha L is e to the minus 20, which is about 2 times 10 to the minus 9. And so multiplying by the other factor, we get 7 times 10 to the minus 9, okay? And then if we had a 40 angstrom barrier, you can see things would be even much smaller then, because then e to the minus 2 alpha L would be e to the minus 80, which is a very small number indeed. It's about 10 to the minus 35, and or 2 times 10 to the minus 35. And so the transmission probability is only 6 times 10 to the minus 35. Okay? And so the transmission drops very rapidly as that barrier gets thicker and thicker. But when the barrier is very thin, transmission is very easy, and we can have conduction across the insulating gap, even though classically this is forbidden. But if the barrier gets only a little bit thicker, then transmission becomes essentially impossible. This last number corresponds to 1 electron every 60 trillion years. I think that's a good description of an insulating gap. Okay. By the way, this problem with aluminum oxide on aluminum is well known. Here, 1 second. Because aluminum is inexpensive, because it's an excellent conductor, and because it's lightweight, it would seem to be a wonderful material for in-home wiring. And for a while, it was thought to be wonderful. Back in the 70s, when copper was very expensive for some reason, people started installing aluminum wiring in houses. But they found that this didn't work out so well. Because there's a problem with aluminum too. The first is, of course, aluminum is flammable. The second is that aluminum provides a nice way to light that fire as well. Because aluminum oxidizes rapidly when exposed to air. And this insulating barrier at the surface gets thicker and thicker over time. And as it gets thicker, the resistance of electrical connections between aluminum wires starts to grow. When we pass a large current through that, there's Joule heating, and eventually the Joule heating might be enough to ignite the flammable aluminum wire. So, lesson learned, I guess, but an interesting application of tunneling.